The next part of transformations that I want to get to is it's called viewing transformations. I want to build up enough transformations so that we can place our models into the world and also define the stationary part of the model in the world, and then figure out how it should look on the screen based on which way we are looking with our eyes. So I got to go through a lot of transformations to do that. It's not a computer graphics part yet, it's a step towards that. It doesn't really talk about how to render the pixels, let's say, but I just need to know what points in my world should be appearing at one particular spot on my screen. So how do I apply all those transformations? So that's the next part I'm going to get to. If you've had a computer graphics class before, you've undoubtedly gone through this chain of transformations before. So let's do that part. So viewing transformations. So in other words, I want to start by putting my entire model into the world in some way. This was the alternate world generator. Should build some model of the world, let's say at a current time. So somewhere in this world I have an object appearing. So some kind of object appears, and I have to take this object and through some kind of transformations figure out where it should appear on a screen, or I guess I should say display. How is this screen or display arranged? Perhaps it goes from 0 to 1080 and from 0 well, let's see, well, I'll just say 1 to 1080 and 1 to 1920, and this can be considered as discretized, just making up whatever coordinates I want here for the resolution. It doesn't matter, but the screen has some kind of resolution, and so we're ultimately going to have to figure out what RGB values to assign. But at today's stage I just want to figure out where an object like this shows up, if at all. So somewhere in this on the screen I should have my face appearing, right? Let's say that shows up in the world. So I want to figure out what these transformations are. I'm not going to talk about how does the light propagate, how does the discretization happen, should this be visible at all or not, or be blocked by something else that's in the way of your view, and correcting for perspective projection. I will get into some of the math of that today, but I'm not going to put the whole thing in together. We'll come back to that at a later part in the course. It'll probably be in the second week when we're covering more of the graphics pipeline issues, and then talk about how those relate to virtual reality, which has its own special set of challenges and problems that are not standard graphics. So all of that becomes part of the rendering pipeline, but today I'm just doing, let's say, the geometric transformation pipeline. So how to do the math of it. So in order to go into that, I'm going to make a rather large figure, but I'd like it to all fit on the board. So let me erase this. So I want to consider the chain of transformations that go all the way from defining your movable models to determining what should appear on the screen. So I just want to go through the entire chain of transformations. I'm going to write it at a high level on the board here and then go through each part. So we talked about the body frame as the way of writing or the way of expressing our movable models. So somewhere in this body frame I'll write X, Y, Z. I have some kind of object appearing here. All right, so some kind of object appears in this frame. We apply the transformations, for example, the homogeneous transformation matrix that I just gave, to perform the appropriate rotation and translation to move that body into the world, or embed that body in the world frame appropriately. So that's one step. I'll draw another frame here. So somehow this, through the transformation, this object, in this case this cube face, gets moved somewhere in the world. Not going to get the geometry perfect here. Of course, this is just an illustration. So this is the world frame. Now, some of the model is already going to be defined in the world frame, right? What part of those were called the stationary model. So if there's buildings, some furniture that doesn't move, maybe trees that remain anchored and don't sway in the breeze, things like that we talked about. This is already defined in the world frame, so there's no transformation. You're already there. And then for each and every one of your bodies that can move, you have to perform a transformation to bring it into the world frame. When you get to that stage, then you can start to talk about how it should look when it appears on the screen, when we get to the later transformations. So this particular transformation here, going from body frame to world frame, occurs quite a bit, right? So I will call this embedding rigid bodies. So it happens many, many times typically. Embedding rigid bodies. There's different names for these if you go looking around. Sometimes this will be called a local frame or sometimes called an object frame. Local frame is more general from mathematics. It shows up in differential geometry and related areas. And object frame is very common in computer graphics as well. So body frame is very common in engineering. So pick what you like. It's the same concept over and over again. And then the world frame ends up, if you use the term local frame, nice word for that is global. It's a global frame. It's the kind of common frame of reference that you'd like to put all of your bodies into. All right, so the next frame I want to get to is called the I frame. I will draw it like this, where Z is going this strange direction, Y is going up, and I will say that X is out. So X is pointing out at you. And then I will have an I here, as the name suggests. So I got too many things in the way here. So X is coming out, but I have an I here with, you can imagine, a pupil right there at the point. The eye will have some field of view, and somewhere inside of that field of view will be this body. Perhaps. Maybe it'll be outside of the field of view. In my example, I'll make it inside the field of view, otherwise you'll just have to eliminate it, or it will not be considered further. So somewhere inside this field of view of this eye, there will be this body, and I'm not really sure how to render it anymore after doing these transformations, but I will just put it in here anyway. So you get the idea. So I need to figure out this part. I will call this the I transform, and also in computer graphics very often called viewing transform or camera transform. But all of these are transforms related to viewing, so I maybe don't want to use that word, but you could call it a camera transform. And what I call the eye could be called the camera. It's not a camera in the physical sense, it's a kind of virtual camera. But you know, when we're using virtual reality, then your eye corresponding in the virtual world becomes like a virtual camera, right? So it makes some kind of sense. So I'm going to call the eye here. So what's essentially going on with this transform is that somewhere in the world, the eye is looking at this. So imagine the eye itself is like a body that appears in the world, right? Imagine we just grab onto an eyeball and we put it in the world and we point it somewhere and we orient it some way, and then it sees something. We would like to then have a transformation that puts the entire world into the perspective of the eye. Right? So it's not going to do any shrinking, distorting, other strange things. It's not even going to decide what's in the field of view or what's not. I just want this transformation to express all of the points in the world in the coordinate frame of the eye. Okay? And then when I've gotten to that stage, I have two more transformations left. So this up here is called the, see, the eye transformation puts you in the eye frame. So we'll do one more at this point, and it'll be called the canonical view transform. I'm going to give some notation to these as well. Let's see. I'll call this one TRB, rigid body. And by T I mean a 4x4 transformation matrix, just like we've been doing. So homogeneous transformation matrix. So TRB, the I one, I'll just call it TI, EYEI, so you remember where it comes from. And I will call this one TCAN for canonical. What we end up with after performing the canonical view transform is a kind of perfect cube centered at the origin. X, Z, Y. I just want to show the whole cube here, and I want its coordinates to go from -1 to 1 for each of the cases. So I don't know where to draw all these. 1, -1, 2. Oops. So this is 1, 1 either way, -1. So Z is going -1 in the back up to 1 because Z is coming outward in this case, and I have X going to the right, -1 to 1. So the origin is in the center of the box. I don't want to draw the origin in there and make more of a mess, but the origin is inside of the box. Why does the box have width 2 instead of width 1? It doesn't really matter, and some people in computer graphics will argue that maybe it should be 1. They're always trying to find ways to simplify the algebraic computations to make them more efficient later, right? In fact, not even simplify is not even the right word. Sometimes they'll make it more complicated so that the calculations are efficient later when it's done in the GPU. So a lot of little funny things are going on like that. But I just want to say that what's happening when you go from this case to this case is the last remaining step left to figure out how objects should appear on the screen is going to be done by a straightforward orthographic projection, which basically means that once you get down to here, the X and Y coordinates have been nicely figured out for each one of your points in the world frame. So from the perspective of the eye. So you've figured all that out. You've figured out the distortions due to perspective projection, and I'll give the details of that, but that's what you've gone and figured out, right? So that's something that's very, very far away. A tree that's very far away should look small on the screen, right? And a tree that's up close should look large on the screen. So those kinds of transformations are being taken into account in this canonical view transform. And then when you're here, all you have to do is take all of the transform objects. They look like they're in a bunch of slices here along the Z direction that are, let's say they're X, Y planar slices. And all the objects just project in a very easy way then to this part, the XY plane, as if this were the screen, except the screen coordinates are usually not running from -1 to 1. They'll be pixel indices, so that requires one more transformation, which to me just looks like a change of units or something. You know, it's very simple because you want your units in the end to be pixels. So pixel coordinates. So there's one last transformation. I would say the canonical view transform is probably the hardest of the ones that we'll do. The eye transform also has something unusual going on. But this final one is quite simple, which is just converting from this canonical coordinates where everything's running nicely, X, Y, and Z from -1 to 1 to the actual pixel coordinates. So this is called the Viewport transform. I'll call it TVP. And when we get up here now, we're finally in some kind of nice screen space. I'm just writing some numbers there just to get you thinking about resolutions. And so this is the screen or display. In other words, you have pixel coordinates. You also have an interesting question of, do you want y to increase as you go down, or do you want it to go in the other direction? Maybe it looks like this, 0 to 767 for example. Maybe it goes in this direction. It depends on how it gets addressed in whatever low level software you have. So you may have it going in one direction or another. I believe for historical reasons y increases going downward, but that doesn't look like nice planar Cartesian coordinates, does it? The historical reasons are, one is, well, we do that for matrices if you noticed, right? Row 1 is up here and row 2 is down here, so we count down this way. Also, if we print lines out on a printer or an old punch card, this increases going down. So I think they went with that. It's just one of these unfortunate cases where that's not the way we would like it in order to make it consistent with the rest of mathematics. So there will always be a little bit of confusion showing up in here as well. You sometimes have to invert the y's. All right, any questions about this? So that's the chain of transformations, unless the question is, can you give me more details, because I'd like to give you more details next, but at this point this is what we have. So again, we start here, define each one of your bodies in its own local coordinate frame, transform them using rotations and translations into this global world frame, and include all the other parts of the model that don't change. Then, based on where the eye is at now, the eye can be moving, of course, in virtual reality. Then we perform the eye transformation so that we get all of this model in terms of the eye's perspective. Then we transform into this canonical view transform so that a bunch of graphics pipeline operations can be performed with ease and efficiency before the final step of just easily projecting them all onto the screen. But we got the coordinates wrong because we put them in this nice canonical form. So we can then do this final viewport transformation, and then we have exactly where my body is that I want to have rendered in terms of pixel coordinates, wherever this might show up. And of course there are discretization issues here, but I'm not dealing with that yet either. That's part of the graphics pipeline. So it's as if these pixel coordinates are continuous variables here at this stage. So I don't mind if this corner ends up being 542.9973, so forth, right? So that'll be quite fine. And then we'll have to deal with problems of aliasing and anti-aliasing to compensate for that or correct for that later as part of rendering. Here we're just trying to figure out where does everything go. All right, so we have this. I'm going to write out the chain of transformations algebraically after erasing this. So this is your last chance to ask questions while this is on the board, because I'm not going to draw this again. Yes?
What exactly is canonical view transform?
So what you're doing in that stage is, let's see. Let's look at the start and the finish. So the start here is I've brought all of the model in the world into the eye's perspective. And that's where you're at here. When you're down here, you've figured out what would go on the screen, and you still have a z depth to all these things that are going to go on the screen. So you figure out the perspective transform. You figured out when you do this transform, and it'll become clear hopefully when we get to it. So in other words, if there's something far away, it will become smaller. When it's transformed into this space. So there will be some objects, let's say, that are far back. They're at a, let's see, if they're far away, then they're at some location like z close to -1. So they're very far away, but I figured out what their size is going to be, so that if I just simply delete the z coordinate, where do they show up in x and y? So everything's been arranged after this transformation so that the scale and location of everything is appropriate based on the perspective transformation due to this eye and the geometry of this. And I have to work that out for you. So this is put in a form that let's say graphics developers can use immediately and perform all the operations they need to determine what's visible from what, is there an obstruction, what kind of anti-aliasing do I need to do, and so forth. So pixel shading operations, things like that, are ready to occur here. I could have jumped everything. I could have taken the x and y part and just made that be pixel coordinates already and skipped this step, but it seems that people like to work in this and do all of their computations in one coordinate system, and then if someone decides to change the display, which as we plug and unplug monitors and do kinds of other things, resize windows and things, then it's only a change of the viewport transform. So it's nice to have this as an intermediate transform. Okay. Any other questions? Yes?
Anything that is not in the ice field of the
Yeah, that's right. When we get to this part, we will have a viewing frustum that is a region that corresponds to everything the eye can see, and outside of that it just will not end up in the box. And then we'll have the problem of culling or clipping when we get to the rendering pipeline, which is figuring out what needs to be thrown away. Yeah. Okay. But when we're up here in the eye part, even though I've drawn the field of view of the eye, it hasn't been used yet. That part will get used, and there will be, I'm going to get to it in just a little bit, but there will be a near plane and a far plane, and that will make a frustum shape that will be transformed into a cube. So, other questions? You're asking the right kinds of questions. You're just anticipating what's coming in just a little bit.
The canonical form is not for one object, but everything will be.
Yeah, that's exactly right. Once we get to the world frame, so this operation TRB is applied to each and every one of your rigid bodies. So they're all put together in this nice place here. You know, it's now you have like a snapshot of the world in 3D, of this virtual world in 3D, or alternate world, let's say, in 3D. Now you figure out what it looks like from the eye's perspective. You have all of it, and then you carry it down here, and the parts that the eye could possibly see are inside of this box. But you have not figured out occlusions yet when you do this trick, because it's just going to be a very simple homogeneous transform. So inside of this box there could be some objects blocking other objects, but that's going to be handled by the rendering pipeline, the graphics pipeline, using this representation. And it will use the z values to determine that. One common technique is called z buffering. It will use the z information for that to do it quickly, to figure out how the pixels need to be ultimately rendered. But today I'm just trying to figure out where should the points go. If you start with a point over here, where does it end up when you get to this? Right? Yes?
So why do we go to the bird thing and directly go from the body plane to the camera?
There's a lot of there are a lot of interesting questions like that, I suppose, where I could say, why don't we eliminate any one of these transformations, right? And so because you see that this is just a chain of transformations, I could just say, why don't I just recognize, which I'm going to do right as soon as I erase this, I'm going to multiply them all together and say, look, it's one big transformation. So each one of these intermediate representations makes it easier to understand what's happening, makes it easier to develop and debug code. And it's especially true for the canonical view transform, as I said, because people might change the resolution and go out this way. It's helpful to have a coherent view of the world. One of the reasons why might be that you could have multiple eyes looking at the same scene, right? If you have a bunch of people together sharing a virtual reality experience, you may calculate this first and then have multiple eye transforms. That's a simple answer, right? But I would find it quite confusing to apply rigid body transforms that automatically take into account the eye viewpoint. I have very much difficulty visualizing that or imagining that. It's mathematically possible. Yes?
Another reason why we want to use the world frame is that there may be many body frames in the world. More than one.
That's right. So that's right. Many bodies are put into the world frame. You're going to have to reason about all of those simultaneously taking into account this view transform. So you could do that, but you know, again, all these things are mathematically possible. I just think that through some amount of experimentation and skill over several decades, people have settled on these intermediate representations to make it easier, clearer for development, to separate everything out piece by piece. So, and Professor Mani is right that if you have many objects here, many bodies, you're going to have to take into account the eye transform for all of them each and every time. This does all the transformations once, and then you just have a single eye transform to compensate, which I find very nice. I figure out where all of you are located in the room in the alternate world, and then I move over here and I look from this direction, and I can figure that out very quickly. And in virtual reality, you're going to be changing the eye very frequently. In fact, you might look at a completely static world and just start moving the eye around, and it's very natural to have this global picture of what's going on. Right. So I'm going to erase this now and then start going into these particular transformations. I do not need to cover TRB, but I do need to talk about the eye transform and the canonical view transform. The last one I'll briefly mention, but it's very simple. Like I said, it's more like change of units or something, like going from meters to feet. So something like that. So I think from your questions you're paying good attention. I think you're anticipating what's coming next. So these are the right kinds of things to be asking. So if we put all of these together, I get a single transformation, let's say T, that is, I got to go in the proper operation order, which as I've just erased it, it was here, and we need to go from right to left across these. So imagine it's still there. So the last one was TVP, the Viewport transformation. The one before that was T canonical. The one before that was TI. And the one before that was TRB for rigid body, which is only applied in the case of movable bodies. Is that right? We had 5 coordinate frames that I showed you, and there were 4 transformations between them, right? So there's one less. So these are the 4 transformations. So we just chain all of these together as homogeneous transforms. I should point out that one of these, the canonical transform, is going to have some non-rigid body transforms inside of it. So it will not be an example of a rigid body transform, but it will be an example of a homogeneous transform. It's just a little more general because it does some scaling due to perspective projection. So it's not going to be rigid, but it's still homogeneous. So before I gave homogeneous only for rigid bodies, just pointing that out to avoid potential confusion. This is standard computer graphics set of transformations. There's a little bit extra that will come in for virtual reality, which I will provide at various points. One of them is that in here we insert TL and TR for stereo rendering. Let's put stereo display because I'm not talking about rendering today. Right? So we have to perform some kind of shift that corresponds to your left and right eye. So when I cover it today, before I get to the left and right shifts, I will consider it to be a cyclopean view. You'll be a cyclops with your eye right in the center between your right and left eyes. And then we will add the stereo part. And another thing that happens, there's another transform here, which I'll call TDIST. And I won't get back to this one for a while. This one, I put dist here for distortion, not distance, distortion, which will compensate for optical distortion. So we'll do some final kind of warping that will account for warping due to wide field of view lenses. So we'll have to do some final operation. It's possible to move this T-dist earlier in the pipeline. It may be advantageous, but it's also more complicated. So the easy fix is just to do it at the end, but there could be some sound reasons for trying to do it earlier, and I'm not sure. I think in most of these virtual reality pipelines in the current state it's at the end here. So it's one final fix to account for the distortion.